Hello everyone and welcome to our webinar on a brief overview of stack-based buffer overflow. I'm Nandini Bharadwaj, the operating officer at CyberWarFare Labs and a host of today's webinar. And I'm excited to have you all here with us today. So let's get started. So before we start, let me tell you a bit about us. We are CyberWarFare Labs, a UK-based company focused on cybersecurity education. Our goal is to help people tackle cybersecurity challenges with practical solutions. Here we have got two main divisions. The first is Cyber Range Lab. So this is where you get hands-on experience with the cybersecurity. And we have built a virtual platform where you can try out real-life scenarios and sharpen your skills with practical exercise. And the second one is upskilling platform. Here we offer a bunch of courses for people at all skills level, whether you are just starting out or you're a seasoned pro. We have got something for you. Our courses cover domains like ethical hacking, red teaming, blue teaming, purple teaming, and cloud security. And recently, we have launched our new portal that is Infinity Learning, where you can log in for free and sharpen your skills in the defensive and offensive domains of cloud security. So I'll share the link with you. You can log in today for free. It's a limited time offer, so you can log in today. And our training services are also available institute, government agencies, and corporate organizations. Both online and offline trainings options are available. So if you want to know more, you can drop us a mail on support@cyberwarfare.live. Okay, so let's move to next slide. So now let's take a moment to introduce our speaker of today's webinar, that is John Surgeon. He's a red team security researcher at CWL. With over 5+ years of experience, he is an expert in reverse engineering, malware analysis, and Windows internal. Currently, he is focused on EV/EDR evasion projects. And as a cloud security enthusiast, John's insights and experience are sure to enrich our discussion for today. So that's all about the speaker. And dear participants, as promised, we are excited to share that every participant will receive an attendance certificate along with the video recording of the webinar. And along with that, at the end of the webinar, John will provide a guide to every participant on how to get guaranteed 80% off on our latest launched course, that is Certified Exploit Development Professional, CEDP. So anyone who is willing to participate in the discount giveaway, I'll be dropping the link with the steps in the chat box. So yeah, thank you for being a part of this engaging session. We'll look forward for your continued participation. And without further ado, I would like John to let's get started. Um, so over to you, John.
Can anyone confirm if I'm loud and clear? Okay, so we will start today's webinar. I hope I'm loud and clear and my screen is visible. Okay. Few weeks back, we talked a little bit about the Stack Overflow and the mitigations that are there in the modern operating system to protect the Stack Overflow vulnerabilities like a Stack Overflow. But here today we are going to shed light on the Stack Overflow, where we will be doing a little bit of the lab exercises as well. And for the content, we will be starting off by reviewing the last few contents that we cover in the last webinar. So first of all, we will start with the stack. So stack is a block of memory that actually holds the temporary data, and it operates in LIFO principle, last in first out. Uh, the uh, the main reason why stack is there is that the program whenever it calls any function, the program needs to keep track of the local variable parameters and everything. In such case, the stack is used in the program, and also stack is a per thread basis, which means each thread owns its own stack. And mostly the stack is used to hold the temporary data while program is executing. And to understand the buffer overflow, we first need to understand this image. If you look at here, this whole image is a stack frame, which means whenever we call some function from the program is going to create a stack frame. So how it goes like is, whenever we call some function, it has to give or pass a parameter to that function. In such case, the parameters are passed on the bottom here. If you look at here, stack always grows to the lower address. So first of all, the parameter will be passed onto the stack, and then the return address will be passed here. The return address will be the location where the callee wants that particular function to return after the function executes its operation. And also it will save the old EBP and the old base pointer for the below stack, which is for that callee function, because after it is returning from that particular function, whichever function it is calling, it has to maintain that frame as well, which is why the old EBP of the callee function will be saved. And right after that, the function prolog is going to create a space where we are going to see, where we will see the stack, where we will see that stack storing the local variables and all the other information that program requires in that particular function operation. Now let's talk about the stack based overflow again. So it's a flaw in a software that occurs when more data is written to the buffer that is actually allocated in the stack. So whenever we pass a huge amount of buffer, and let's say the allocated space in the stack doesn't hold all the cannot fit all those buffer, in such case it will overflow the adjacent memory regions. By adjacent memory region means that there could be other important informations like the variable in the program, sorry, that particular function, or the return address which we saw here, the return address, saved EBP, or the parameter itself, everything adjacent to that particular space, it will be overwritten. And mostly in the vanilla stack based overflow, the idea here is to override the EIP, which is an instruction pointer register. And how they control over the EIP is by overwriting the return address. If you look at here, this return address, so if attacker manage to override this return address with their own controllable location, then they can redirect the program flow from here to some other location where they control it. And that is what we are going to perform in the lab today. So here, let's look at this stack frame again. Here it has saved the return address where it wants to return after the function operates, and there is an old EBP, and the space is allocated here. If you just visualize this diagram here, and if we overflow this, then we will end up overflowing everything here in the adjacent memory as well. So this is just the space that could be allocated for the stack, but if we manage to feed in more data, then it may end up overwriting everything that is adjacent to the memory, which means overwriting the return address itself. And there are some trivial C functions that may lead to the overflow, like a get, string copy, string cat, mem copy, mem move, sprintf, and there are many others as well, depending on the arithmetic operations, the loop. So many way the program could lead to the overflow. But here today we are going to um, perform the very vanilla based stack overflow where no mitigations will be available in that particular program. We will figure out where the vulnerable code location is, and we will figure out how the offset. We will figure out the offset to the return address, and we will we will end up overwriting that return address with some controllable location, most probably pointing to our payload. And we will, after crafting the buffer, we will send that buffer to the program, and hopefully we will see our exploit getting executed, or maybe our shell code getting executed after the successful craft of this exploit. Okay, so we will now move to the lab area. I hope the lab is this lab video. The window is visible. Just a second. Can anyone confirm that the Ubuntu machine is visible? Okay. So today we are not going to reverse the binary. We are simply going to go through this dummy code, which we are going to exploit in this lab. If you look at here, this is just a normal server which simply echoes the whatever the name is given to that particular server. If you just go and look at here, it is a server, and here, while handling the response, it is reading the response from here from the socket, and then just adding the hello in front of that particular buffer, and then sending back again to the client. So this is what actually this program does. And if you look at here the code, the vulnerable code here is the ascent printf. Why? It's because it is actually, if you look at here, the greeting message has the size 100 bytes, so it can only hold the buffer up to the 100 bytes. But here we are actually copying all the buffer that it is receiving from the client, which means it will concatenate the buffer that has been received from the client, and then it will try to move all the buffer to the greeting message. But the greeting message having 100 bytes of the size, it won't be able to hold all the buffer that we are sending, and there is no length check, nothing at all. So mostly the uh, mostly these functions are, yeah, definitely these functions are likely to be vulnerable, but also it comes with a bad coding practice as well. If there is no lane checking or no input sanitization, then these function leads to the overflow. So our goal here is to overflow this greeting message and override the return address, and take control over the execution to execute our payload. So to do that, first of all, since it will take time, which is why we already have the crafted scripts here, just to avoid ourselves um, from getting into the rabbit hole while writing the script. Just to save the time, we already have written the script here. I will simply go through the script and explain what it is actually doing. So first of all, our goal is to crash the program and understand what's actually going on and how we can control the return address. And make sure you disable the ASLR with the echo 0, and in the randomized VA space inside the proxies kernel, we are just appending this 0 value here just to disable the ASLR. Okay, so the value is overwritten here is 0, which means we have disabled the SLR in the entire system. Here is our server. I will simply execute the server. Okay, the address is already in use. Okay, here is the server, and if I just go and do netcat, and the port here we have set is 8080, and if I just type my name here, the server is going to give us our name back with saying hello and the name. And in the server side, if you see here, it has written that it has received the name and it is sending the greeting with hello John. However, if we do, however, here we know that if we send more than 100 bytes, it's going to crash, which is why what we are going to do is we are going to send more than 100 bytes. It's 100 byte in hexadecimal. I hope this will probably crash the application. And there we go. The program is crashed now because we sent more buffer than actually it can hold on to. Now, how we can exploit this scenario? So at this point, we have no mitigation enabled in this machine and the binary itself. So it's quite easy to exploit. So first of all, our goal is to find the location where the return address is. So we have to calculate the offset to the return address. To do that, we are going to open the program in the GDB, and we are going to run this program. Okay, the address is already in use. Let me. Okay, now it is waiting for the connection. So first of all, we are going to send the random bytes here. So if you look at here, this is a random pattern of a huge size. I think most probably 200 2000 bytes in hexadecimal. We are going to send these patterns, and how we generated these patterns is with the help of the one of the tool from the Metasploit called pattern crate. There are many tools that you can make use of to generate such patterns. So all you have to do is go to this location. So all these scripts will be provided to you if you want to do it on your own. So just go to this location, So this is how we generated the random pattern from the pattern grid. And once the pattern is generated, all we have to do is to come here and paste it here. And why we are generating this random pattern is, if I don't do that with the random pattern, let's say I just want to do this with the, I'll copy this, and from the netcat, if I send this buffer again, all a junk byte, which is larger than the 100 bytes, here you can see the EIP has been overwritten by the 414141, which is all A's. And we have overwritten the EIP, we have control over the EIP, but we do not know what location from where this actually A has been overwritten to the EIP. We need to know exactly, so that we can, instead of the 414141, so that we can write something really valuable address, so that we can point this address to somewhere else in maybe to our cell code. So to do that, we have to have this random pattern. Okay, we will re-execute the program again, and then we have a small script here which is actually going to send the random pattern to the server. So first of all, we are going to run this script, find RIP, where we are just sending random patterns, and to see which pattern will get will the EIP will hold, which random character it is going to hold. We are going to check that out. Okay, most probably we have sent that. And if you look at here, the EIP is now holding the value 7AD8. So let's copy this and let's go over here. So once we have find the random value which has been overwritten, we just have to copy here, and then with the help of the pattern offset script, we have to query this value. And if we query this value, it will give us the exact offset where this is actually located. And it is located at offset 113, which means after sending 113 bytes of this junk value or any value, the data that will be overwritten will be the return address. So to confirm this, we have another script which is control rip.py. And if you look at here, the A, I'm sending the A value 113 times, like as we have like as we have received the offset value. We are depending on this pattern offset and just taking 113 value to send the A bytes, and right after that, this is the return address. So this B value will override that return address, and next time when we see in the RIP after sending these bytes, we will see BBBB, not 788. We are going to send that exploit now again. 113 bytes of the A value, and then 4 bytes of the B value, and some knob bytes just for the padding, and just for the padding purpose we are sending 9 knob bytes, 20 knob bytes, that's all. And this is control rip.py. If I send this and go and see in the debugger, you will see the EIP is now pointing at the 42424242. Okay, we know that now if we send the 113 bytes and whatever the 4 bytes after that is the return address, and if we override that with some value, it will be pointed by the EIP. This time 424242 is what we actually override that return address with, but this time instead of the 424242 we are going to write with the address which we actually control. And right now all the mitigations are disabled. If I do check, you can see all the mitigations are disabled, so we don't have to worry about bypassing any of the mitigation. In that case, if you look at the stack here, if ASLR is not enabled, the stack location will be almost the same that as we have seen here. Definitely GDB outside the GDB and inside the GDB there will be little offset. um, you will save little bit in the stack. However, wherever you point at, it is it will be the stack location, because we know once the SLR is disabled, the stack is non-randomized, so we can select one of the stack address and try to point at the cell code. So here in this case, instead of pointing at the 424242, we will point at some address, most probably let's say this address. So if I copy this, so if you look at it, FFFD190, I don't want to override here, so let me just copy this again. So instead of B, if I write, let's say I don't want to write the address B, instead I want to write the address FFFD190. Let me copy this and paste it here. And let me rerun the program again. This time, okay, let me do one thing. This time I'm going to put the breakpoint at here. Most probably I have forgotten to mention the socket reuse here in the program, which is why we are getting this address in use issue. Let's try it out again. We have to wait for a while. Let's try to run this program again. Okay, it is still in use. Let's run this program. Okay, now it is waiting for the connection, and we have set the breakpoint at the FFFD190 because at this point the stack is executable, which is why it is going to execute this from this address, which is why we set the breakpoint here, just to confirm that we can control this location. And we do Python 3. Let's send this. And then we already slipped away from that location, but if you look at here, the EIP is at 19 9F, which means after it has stopped after the knob bytes. So it has gone through all the knob bytes. We can also do copy, breakpoint, Control V, run this again. Let's see if the port is killed. Okay, we have to wait for a few seconds before the port will be available to reuse. So I'll first put the breakpoint at that location and rerun the program again. And we send the Python 3 control to stack pi. And if we send this, okay, it just slipped away from that location. But definitely, if you look at here, it has stopped here after the knob, which means we control over the EIP and it executed everything and then it stopped right here when the EX is not a valid address, which is why it stopped here. EX is just B7 here, which means instead of this 195, we can actually have a cell code here, which will end up executing this cell code rather than this knob values here in the program. Sorry, some random junks here in the program. We are going to place the cell code here. To do that, we have the final exploit here. So it is same. We have selected the address FFFD1E0, which is a stack, and it is written right after the 113. And then there are 20 knob bytes for the padding, and right after the padding there is another um, data that we are feeding here, which is a reverse shell, and you can generate this reverse shell with the help of the MSF Venom. So right now it is going to connect to the port 999 at the IP address. This is the IP address of this machine, and this is the shell code that we are going to send. And for the for let's say sometimes if you only send the shell code and you send nothing here, in that case the program may crash because of the junk bytes there. So to fix those problem, you can have a small number of the knob bytes. Most probably 4 to 5 will work, but here we are sending 20 bytes of the knob bytes. So this is how the structure looks like. Now for now, we are outside the we will be seeing that inside the GDB, which is why we have to change this address. Because I will tell you why I'm doing this. So let me comment this out for now, and then we will put a breakpoint at 190, which is why we are going to copy this. Okay, run the program again. Let's kill the port. Let's wait for a few seconds until the port gets available for us to use. Okay, now it is waiting for the connection. We'll put the breakpoint at this address where we want to control our execution, which is FFFD190, where the NOP code are present, and continue the program again. And then we will send the exploit. And as you can see here, okay, the address has been most probably shifted to the different location. Let's see, D190 FFD. Okay, it actually executed the program, and it also executed the shell code, which is why it couldn't find that location, find that port to connect at. All we have to do is go back again here, open the port at 999, which is where it is going to connect, run this program again. Okay, control C. We want to breakpoint at this. Even if we miss the breakpoint, it shouldn't, but even if we miss the breakpoint, it could connect to um, this listener. Let's see. Let's continue the program again. And here we are going to send the exploit. And there we go. The breakpoint was not able to trigger. However, we already connected um, to the to the to the open port. It is already connected. We received the reversal. However, the program has already been terminated because we were running inside the debugger. To fix this issue, because we cannot do this outside the debugger, the stack value will change. At least we noticed that there has been a connection on this listening port. Now we have to make sure that we will do this from outside of the debugger. To do that, let's do server. Let's wait for until the port will be free to use. Okay, there we go. Now let's send the exploit. We send the exploit and it crashed. Sorry, we forgot to listen on the port. However, it crashed, and let's see why it crashed. If you look at here, this is the EIP where it is pointing at. Let's copy this and see what is in here. If you look at it, it is pointing at some random location where the a byte is FF. However, we want this to point at the knob bytes, which means changing this address will be helpful. So we have to figure out which address we can use to land perfectly on the knob slate. We will use the E0 here. So EF is pointing at here, and E0 is between the DF and the EF, which means we will be selecting the E0. Let me copy this, and let's do E0. Okay, the server is running, our listener is listening, and here this is the location where our knob bytes, these knob bytes will be present. It will slide through this 20 knob bytes and reach to the cell code, and the cell code will be executed, and we will be seeing the reverse connection here. And there we go, we have the connection received here. If I do ID and who am I, it is going to execute the code here. So this is how we control the execution, and we made sure that this is going to execute our cell code. The cell code was executed, and we received the connection here. So this is for this lab, and here are almost everything's are detailed here. So we will be providing this script. You can play around with this script. Okay, so let's get back to the slide again. So let's go to our hot topic today, which is providing the 80% off in the CEDP course, Certified Exploit Deployment Professional course. So to get the 80% off in this course, all you have to do is go to the link which we will be providing. You have to play the quiz, and after I think this is most probably the link. After playing the quiz, you have to score 80%. Once you score 80% in that particular quiz, you are going to get a coupon which is actually going to give you a 80% off on that particular course, which is a CEDP course. And thank you everyone for joining this webinar. I hope you enjoyed this webinar. This is all for today. If you have any question, then you can ask. If there are any question, you can drop. I will be here for 3 minutes, and then we will end the session. Yeah, definitely you will get the recording of this session as well as the labs and all the codes which we use in the lab. You will be provided with that as well. Yeah, it will be sent through the email as well. Let me do one more thing, just to make it more easier. So here in the chat, if it is visible, I will pin the link here for the quiz. Can you check whether you can see the link to the quiz? Okay, I hope you enjoyed the webinar. I think it's time for us to put the end on the webinar. If any questions, I'll be here for one minute. Okay, everyone, thank you for joining this webinar. and soon we will come up with a more exciting webinar as well. And thank you everyone for taking out your time and joining this webinar. Your time will be valuable to us as well. So I'm ending the webinar now. And good day, everyone.